Fluorine is in your toothpaste. Fluorine also reacts with glass, concrete, and water. It reacts with platinum. It reacts with noble gases, the elements specifically named for not reacting with anything. It does not bond gently, it attacks. And it is the only element on the periodic table that spent 70 years killing the chemists who tried to isolate it. That is not an exaggeration, that is a body count. The periodic table has 118 elements. Most of them have preferences. Sodium likes chlorine. Oxygen likes almost everything. Carbon builds structures. But fluorine does not have preferences. Fluorine has a compulsion. It is the most electronegative element that exists. Electronegativity is a measure of how aggressively an atom pulls electrons from other atoms. On the Pauling scale, fluorine scores 3.98, the maximum. No element in the universe pulls harder. Every atom that comes near fluorine loses an electron to it. Every bond fluorine forms is a surrender. Here is why that matters. Chemical reactions are, at their core, about electrons moving between atoms. Most reactions require energy to start. A spark, heat, a catalyst. Fluorine does not wait. Fluorine reacts on contact, at room temperature, in the dark, with almost anything. Steel wool bursts into flame when exposed to fluorine gas. Glass, which resists most acids, is eaten through. Water, the most stable molecule in everyday life, burns. Not a metaphor. Fluorine displaces the oxygen in water, releasing heat, producing hydrofluoric acid and oxygen difluoride, both of which are toxic. The water is gone. What remains is worse. The first person to suspect fluorine existed was Carl Wilhelm Scheele in 1771. He was working with a mineral called fluorspar, calcium fluoride, and he noticed that when he treated it with acid, the vapor that escaped etched glass. Something in fluorspar was extraordinarily reactive. Scheele could not isolate it. He was already dealing with the consequences. Hydrofluoric acid, one of the byproducts of his experiments, is not an ordinary acid. It does not just corrode surfaces, it penetrates skin, reaches bone, and strips calcium from the body. The damage is often painless at first. By the time the pain starts, the injury is deep. Scheele died in 1786. The official cause was mercury poisoning from his other experiments. But his work with fluorspar left a trail. Over the next 100 years, at least 2 chemists died, and several were permanently injured attempting to isolate the element that was producing those reactions. Humphrey Davy tried in 1813 and poisoned himself so severely he was bedridden for months. The Knox brothers in Dublin attempted it in 1836. Both were hospitalized. Jerome Nichols died from fluorine exposure in 1869. George Gore managed to produce a tiny amount in 1869 as well, but the fluorine immediately reacted with the hydrogen in his apparatus and exploded. Every attempt ended the same way. The element destroyed the equipment, the container, or the chemist. The person who finally succeeded was Henri Moisson. Paris, 1886. Moisson understood that the problem was not the chemistry. The problem was containment. Fluorine reacted with every material used to hold it. Glass, ceramics, metals, all failed. Moisson designed an apparatus made of platinum and iridium, cooled it to -50 degrees Celsius to slow the reactions, and used electrolysis to split hydrogen fluoride. On June 26, 1886, he collected a pale yellow gas. It immediately attacked the platinum electrode. But he had enough. He had isolated fluorine. The Nobel Committee gave him the prize in 1906. He died 2 months later, at the age of 54. His colleagues attributed his early death to the cumulative damage of working with fluorine compounds for 20 years. And this is where it gets interesting. For decades after Moisson, fluorine remained a laboratory curiosity. Too dangerous, too reactive. No industrial application could justify the risk. Then 2 things happened. The first was an accident. In 1938, a chemist named Roy Plunkett at DuPont was experimenting with refrigerant gases. He stored tetrafluoroethylene in a pressurized cylinder, came back the next morning, and found the gas was gone. The cylinder weighed the same. The gas had polymerized overnight into a waxy white solid that was slippery, heat-resistant, and chemically inert. Nothing stuck to it. Nothing reacted with it. DuPont called it Teflon. It was fluorine, domesticated. the most aggressive element on the periodic table, locked into a polymer chain, suddenly became the most passive surface you could manufacture. The second event was not an accident. It was the Manhattan Project. Building an atomic bomb required enriching uranium, separating the fissile isotope uranium-235 from the much more common uranium-238. The method they chose was gaseous diffusion. You convert uranium into a gas, push it through thousands of barriers, and the lighter isotope diffuses slightly faster. The only compound of uranium that exists as a gas at reasonable temperatures is uranium hexafluoride. 6 fluorine atoms bonded to 1 uranium atom. The entire enrichment process depended on fluorine. The problem was that uranium hexafluoride is extraordinarily corrosive. It destroys standard piping, seals, and valves. The engineers at Oak Ridge had to develop entirely new materials, new gaskets, new coatings, just to move the gas from one building to another without the infrastructure dissolving. Fluorine did not care that it was wartime. Fluorine does not negotiate. Now, the toothpaste. Sodium fluoride has been added to municipal water supplies since 1945, and to toothpaste since the 1950s. The chemistry is straightforward. Your teeth are made of hydroxyapatite, a calcium phosphate mineral. It is hard, but it dissolves in acid. Every time you eat, bacteria in your mouth produce acid, and your enamel erodes slightly. Fluoride ions replace the hydroxyl groups in the enamel, converting hydroxyapatite to fluorapatite. Fluorapatite is harder. It resists acid better. Your teeth last longer. The amount is tiny, about 1,000 parts per million in toothpaste, a few milligrams per day. At this concentration, fluorine is protective. At higher concentrations, it is toxic. The margin between helpful and harmful is narrower than most people realize. And that is the paradox. The same property that makes fluorine destructive is what makes it useful. Its extreme electronegativity means that once fluorine bonds to something, it holds on with extraordinary force. The carbon-fluorine bond is one of the strongest single bonds in organic chemistry. That is why Teflon is so stable. That is why fluorinated compounds resist heat, resist solvents, resist biological degradation. And that is why PFAS, the per- and polyfluoroalkyl substances used in non-stick coatings, waterproof fabrics, and firefighting foam, do not break down in the environment. They are called forever chemicals for a reason. The same bond strength that makes fluorine chemistry useful makes fluorine chemistry permanent. The chemistry does not care what you intended. It does what it does. There is something almost comedic about fluorine, an element so aggressive that it spent a century maiming anyone who tried to touch it. And we solved the problem not by understanding it better, but by trapping it. Teflon is fluorine in a cage. Toothpaste is fluorine on a leash. PFAS, or fluorine, that we let loose again without thinking about what happens when a leash has no end. The most dangerous things are not always the ones that hide. Sometimes they are the ones we domesticated. We brought fluorine into our kitchens, our drinking water, our mouths, and it is behaving, for now. But the bond it forms, with our teeth, with our pans, with our groundwater, that bond does not break. That is what fluorine does. It holds on, and it does not let go. Fluorine hates everything. That is what the textbooks say. But there is one thing in the universe that refuses to react. Not because it is strong, because it is complete. It is a different kind of chemistry, and it is for another time.